Hey, what's up guys, my name is the Cherno. Today we're going to be taking a look at Unreal Engine 5's new amazing demo. So yesterday I woke up to like a lot of messages on every platform telling me to check out this amazing new demo that Unreal Engine has released, and I thought that it would be fun to give you guys my thoughts on this. And I have actually seen it once before, so this isn't going to be like a completely new like reaction video or anything like that. It's more going to be my kind of thoughts on this video. But the time that I did see this was quite brief, so this is going to be a little bit more of me taking my time, enjoying the video, and just letting you know what my thoughts are. I'm actually really excited to look at this more closely. Now, for those of you who don't know who I am, I like to make game engines. I worked as a software engineer at EA on various game engines. First, I worked on EA's primary mobile game engine called Osiris, and then later Frostbite. In fact, see, I have the Frostbite pen. This is all I have now. And then I quit all of that because I wanted to work on my own game engine called Hazel, as well as make YouTube videos for you guys. So that is what I am focusing on now. Okay, so without further ado, let's dive in and take a look at Unreal Engine 5. Also, I'll have the link to this video, of course, in the description below.
Hello, I'm Brian Karras, Technical Director of Graphics here at Epic Games.
Hi, I'm Jerome Plateau, Art Director of the Special Project.
I just want to say that straight away, this kind of engineer-artist pairing just completely reminds me of my life. So back at EA, I did a bunch of like various media things because of course I have a YouTube channel, I can edit YouTube videos and all of that. And I had a friend, and I'm still friends with actually, the technical artist that we had on the team. And the two of us would always do things together. We made various like silly videos for like internal EA use. We even went to GDC together in San Francisco. It was a good time, and this is just, it's just so nostalgic.
A few years ago, we got together as a team and brainstormed where we thought we could push forward the state-of-the-art in real-time graphics. There were two key areas that stood out. The first, dynamic global illumination.
Yeah, dynamic global illumination, so GI. This is definitely one of the areas that probably needs the most improvement in. In fact, this is something like doing GI dynamically is something that the industry has been trying to do for a very long time. It's actually one of the big reasons why we're separated, so to speak, like fidelity-wise with like the film industry and offline graphics. Because what global illumination is, for those of you who don't know, is more or less a simulation of how light bounces in the real world. So light doesn't just kind of hit an object and then completely disappear. It bounces off an object and then hits another object, and this kind of culmination of light bounces is what gives every object you see in the real world its color. Now in offline graphics and like visual effects for movies and all of that, they're able to use ray traces, which is basically a very realistic way of rendering something, but it's very, very slow. And using a ray tracer enables you to calculate the light bounces perfectly. However, in real-time graphics, that's not really possible to do at the same scale. That's why there's so much buzz about all of this kind of real-time ray tracing stuff, this RTX stuff. It's amazing because it lets us do certain ray tracing kind of tasks in real time. It can give us perfect reflections, or possibly more importantly, not perfect reflections, meaning kind of blurry reflections, which are very difficult to do otherwise. It can give us beautiful ambient occlusion. It can give us absolutely perfect shadows. All of these things we can now kind of do in real time, but it's not really anywhere near at the same scale. In fact, we rely on a lot of kind of denoising algorithms to try and make the scene look good because of the low amount of samples or rays that we're able to actually calculate. So because of all of this, global illumination, which, you know, requires ray tracing essentially, it's very difficult to do that. And we have a lot of approximations that try and kind of, you know, simulate this light influence, but ultimately it's very difficult. Now, doing all of this offline is still something that the industry does quite a lot, meaning we can take our time to calculate absolutely perfect global illumination for a scene and then bake it into some textures, which we can then just sample at runtime. It's very, very fast, but it means that everything has to be static. We can, of course, have multiple kind of versions of these, so we could have like a morning scene, an afternoon scene, an evening scene worth of like global illumination. But if a scene changes dynamically, that data is useless, meaning that like maybe if we have like a cave and then a rock kind of moves off and reveals all this kind of light entering the cave now, and that has to all bounce around the cave and give it kind of that ambient lighting, we can't really do that. That has to be dynamic, and that's what they're talking about here.
Beautiful bounce lighting instantaneously.
I don't have to be constrained to do a game where the world has to be static. And I'm able to iterate a lot faster.
And
yeah, that's important as well. It's not even about like making stuff dynamic. Even for a static world, if you're able to kind of change the lighting as you're working on that world and see it kind of, change instantly, that also is kind of quicker iteration times. It makes the development of the game a lot faster because you don't have to wait hours for your computer to figure out where on earth the light bounces are going.
Call this new system Lumen. We're about to show you what it is capable of. But first, there was another area that we thought we could push forward. Truly virtualized geometry. The artist wouldn't have to be concerned over poly counts, draw calls, or memory. We could directly use film quality assets and bring them straight into the engine.
And that's a big deal for artists. I just want to be able to import my ZBrush model, my photogrammetry scan, my CAD data, without wasting any time optimizing, creating LODs, or even lowering the quality to make it hit frame rate.
In the end, that's what it's all about.
That's what I like about this as well. By the way, everything I've heard so far, it's not just like an end result in terms of visual fidelity. These are actually workflow improvements. That's a big deal because if artists can spend less time doing like manual labor tasks, such as reducing the poly count of a very high quality model, they can just put it in and let the engine take care of it automatically. That's honestly amazing. They mentioned photogrammetry scans, and that's actually a really good example of this. If I go out with my camera and just take this amazing, like high quality photogrammetry scan of like a rock in the real world, that's great. It's gonna look amazing, but I can't really use it in the context of a real-time application or a game because it's just too high quality. So I have to go in, I have to kind of remove everything. Doing this automatically can sometimes lead to a lot of visual artifacts, so it's good to just try and clean that up kind of by yourself. But the fact that you have a rock with like millions of triangles now and you have to spend time cleaning that up, it takes the fun out of everything. Who cares about this rock? Like, I'll just build a rock from scratch, Sorry, environmentally realistic rock. I can't use you, man. You're too good. So this is good.
Art that just works. And we call this new technology
art that just works.
Nanite.
That's brilliant.
Here is
Nanite.
the future of Unreal Engine running live on a PlayStation 5.
All right.
So let's take a look at it.
All right, so I don't know the specs of a PlayStation 5. Off the top of my head, I know that they're supposed to be quite powerful, and I also do want to emphasize the fact that it is new hardware, which means that I'm sure that they, on one hand, they probably couldn't do amazing work with it, that they will be able to 5 years from now, because, at the introduction of any new platform, it takes a little bit of time to get used to it. But on the other hand, since it is a dedicated piece of hardware, if they were provided with very good specifications and, they probably collaborated with Sony on this and they spent a lot of time on this, then potentially they could extract a lot more performance from this than from just a PC. And the reason is that if you're running on dedicated hardware, which I imagine has ray tracing cores and all of this other dedicated hardware, I guess, then it's actually easier to optimize for that, because if you know exactly what hardware you're running on, then you can specifically optimize for that hardware. So I'm kind of torn. On one hand, PlayStation 5, okay, that's cool, it's new hardware, but on the other hand, since it is a specific piece of hardware, there's a lot of optimization potential there as well. By the way, I have so many things to say that at this rate, I feel like this is going to be an hour long, so I might just keep it a little bit more, not as detailed.
Has to be the right way.
Wow. Right off the bat, this kind of reminds me of the photogrammetry style tests that Embark were doing on Unreal Engine. I guess maybe just because of the aesthetic. But looking at this scene, immediately, the detail is absolutely astounding. It looks like it definitely could be an offline render. Ooh, and the sound. The sound is really nice.
Before we continue, let's stop a moment and take a look at some of the key features of this demo. Much of what you see was built with Quixel Megascan assets, but instead of using the game versions, we use the cinematic versions, which would typically only be used in film. There are around 1 million triangles each.
Wow.
And thanks to virtual texturing, they all use 8K textures as well. Nanite can render an insane number of triangles very quickly. There are over 1 billion triangles of source geometry in each frame.
Billion with a B.
That Nanite crunches down losslessly to around 20 million drawn triangles.
Okay, 20 million. That's still quite a lot.
What does that many triangles look like?
I mean, maybe a PS5 can handle that, but wow, okay.
This isn't noise.
So this is...
These are the...
These are
The triangles,
triangles.
each a different color.
Each different color. Yeah, so what you're seeing here is essentially like an ID of a color ID of each triangle here. So each one of these colors represents a different triangle. It's probably not enough colors in an 8-bit color to represent this. Actually, yeah, 20 million. Yeah, there's not even enough colors. There's not even enough individual colors available to us to actually visualize all of these triangles. So they're probably having to reuse colors. Yeah, that's a lot of detail. The thing is, with triangles in general, like they mentioned that, it was over 1 billion triangles. Like that's all great, but the reality is that, if you're rendering to like a full HD display, for example, that's only about 2 million pixels. And a 4K display would be, well, 4 times that, so like 8 million pixels. If you have that many pixels and you have 1 billion triangles, then, if each triangle takes up 1 pixel, that's still too much data. So what they're having to do here, I imagine, is some kind of dynamic like level of detail algorithm or something that's actually able to work out what triangle of this kind of 3D model is going to have the most influence on the outcome of the scene. And that's probably the triangle that they end up picking. But again, because it ends up being so small in this scene. Like these triangles are tiny. Some of them you can kind of see. Like, these triangles here obviously are quite large. You can see they're in the shape of triangles here, over here as well. But most of them, since they're far away, are just 1 pixel large. And if they've got a good way to kind of cull that list of triangles down and obviously have a really good data structure that, is very cache friendly and all of that, so that they can actually iterate through those triangles and get the right data for each triangle as fast as possible, then they have to work out what triangle to keep, what triangle to discard, and essentially what data from that set of vertices they actually want to keep and then use in different calculations that would be done in a shader, such as, sampling from textures, lighting equations, all of that stuff. So lots of work going on here.
They're so small that they look
sure.
like noise. Nanite achieves detail down to the pixel, which means triangles are often the size of pixels.
Yeah, exactly.
This amount of geometric
Really cool.
detail requires shadows to be pixel accurate as well, and Nanite can do that too.
Yeah, I do really wonder how they're doing shadows specifically. They mentioned that Nanite does that, which is the virtualized geometry thing, but I guess that since a lot of this is done kind of in a per pixel basis, they're just able to, you probably use those billion triangles when trying to work out what is occluded by, what occludes the light source and what causes a shadow.
Speaking of lighting, all of the lighting in this demo is completely dynamic, with the power of Lumen that even includes multi-bounce global illumination. No light maps, no baking here. Without GI, all of that
Okay, so this is without GI. See, so this is just like a directional light with like a shadow caster. No bounce lighting at all, meaning that once the light hits a surface, that's it. The light disappears. And you can see that it looks terrible. It looks completely dark. You can't see anything because the rest of what you're seeing,
beautiful
which
lighting
I imagine
is
they'll
gone.
show in a minute.
With Lumen enabled,
There you go. That is all of that light bouncing around this entire environment. All this ambient light is actually calculated by, I guess, in some way simulating or tracing how the light bounces off the surfaces that it does directly hit.
can move the light and the bounce changes instantly.
Okay, this is interesting. So they're talking about the bounce changing
With
instantly.
Lumen enabled, we can move the light.
But I can see here that if I go frame by frame, you can see that this area, as it changes, doesn't immediately change. It kind of fades out. And it's difficult to say whether this is a deliberate visual effect to make the light transitions seem smoother, which it very well could be. But also what they might be doing is taking a couple frames to actually recalculate this new bounce lighting. So the bounce lighting can still be dynamically calculated and baked into some kind of light map, and then obviously applied. That way it's kind of cached and you can keep reusing it without having to calculate it every frame, which, I imagine they probably would be doing some form of that. And then, maybe if that lighting calculation takes, a couple 100 milliseconds or a couple frames, they can kind of keep reusing the old ones while the new ones are being generated. And that way, it doesn't change instantly, but you get a transition. But again, they could be doing all of this real time. I don't know. It's just that kind of fade seems a little bit interesting. But they are saying it's instantaneous, so maybe it is.
Move the light and the bounce changes instantly. Okay, let's keep going. We've made some great additions to our audio system as well. Convolution reverb allows us to measure reverberation characteristics of real spaces, like actual caves that we sample, and reproduce them in virtual spaces.
So this is really cool. Like, first of all, I just want to point out that audio is a huge deal. Like, if you guys watch this demo muted, it will feel completely different than if you watch it with headphones and, you know, completely. It adds so much immersion. Like, audio is incredibly important, and I do not doubt for a second that if they had not gone with high quality audio and all of this fancy audio kind of technology, that this just would not feel anywhere near as good. They also mentioned sampling like real world reverberation. That's really cool and that's really useful because, you know, with physically based rendering, what people have done is they've kind of gone ahead and sampled how light reacts off of different surfaces in the real world and how it like bounces off that so that we can then use that in our physically based materials. And that's part of the reason why rendering looks so good now. So the fact that they're kind of doing that same process essentially for audio, they're able to actually measure reverb characteristics in like real world caves and see how that reacts. That's really cool, and that's definitely going to bring a whole new level of realism to this kind of stuff.
Sound field rendering allows us to record and play back spatialized audio.
So good.
All of this adds up to a more immersive experience.
Yeah, I don't doubt that. Animations are really on point as well, by the way. Like, all of this stuff, like, feels really good. And actually, I really like the kind of, you can see that this kind of shadow here is kind of, it's a little bit red as well. It looks like it's kind of blending in with the subsurface color, which is, again, really, really nice. And definitely adds a whole level of realism. You can see the light going through her fingertips and all that subsurface scattering here is kind of making all of this, you know, all her hands here look a little bit red, and that goes a long way to making really good kind of realistic looking skin. So they've done a really good job on that as well.
This swarm of bats was created with our Niagara effects system. Particles in Niagara can now talk to one another and understand their environment like never before.
Yeah, the sound is amazing, first of all, but then also all the particles
We've also added a
really
ton
cool.
of new functionality to run fluid simulations like you see in the water below.
I have to say that so far, I think the worst part of this demo is the water. I mean, it doesn't look terrible, but I don't know, people like, you know, characters wading through water, that's been done better before. But, you know, I mean, technically, though, they could be running this on a completely different level of simulation, so it's less static, and, you know, maybe that's why.
The demo runs on our chaos physics system. Here we are using it to accurately simulate the rigid bodies of the falling rocks and the cloth of her scarf.
Yeah, I imagine that each one of those rocks is probably completely like a physics body and reacts to the environment like it should, which is really cool. And of course, the characters always have some kind of scarf or like a cape or something on to get that cloth physics in there. I love the ambient particles floating around, the ones that don't really collide with anything, but that goes a long way for like visual fidelity as well.
Now that the environment is so complex, we've needed to greatly improve our animation systems to adapt. We've added predictive foot placement and motion warping, which dynamically modifies IK and body position to look more natural.
That's so true as well. I'm glad that he mentioned that, you know, because they've come a long way in other areas, they now need to come a long way with their animation. Because again, like if you have not so great looking natural realistic animation, but it just looks realistic, like everything you're rendering looks realistic, but your animation isn't, it's going to completely just destroy your whole scene. So this animation looks very good. And I think that's also very important.
For the character to more realistically interact with the environment, we've added the ability to trigger seamless contextual animation events, like her hand on the door.
Looks promising.
Yeah, so the fact that she's able to put that put her hand on the door, and that's obviously not like a pre-made animation. That's just a contextual animation that the kind of animation AI has probably figured out based on the context of where she's moving and how she's moving through the scene. I think that's, that's incredible. And using that kind of procedural AI animation really, I think, is the future because, for example, if your character's wounded, maybe they've been like shot or something and they're like staggering and they're just grabbing onto like nearby objects because they can barely walk, that's going to go a long way. And I think that that's really cool.
Dynamic GI is amazing, not just for speeding up iteration, but also for its impact on gameplay. Any light source can move while still...
Yeah, see, like, the fact that I don't doubt that this scene is completely dark. There's no light sources. There's no ambient light in this scene at all. It's enclosed. The only light source entering from the outside is quite far away, but she's got this kind of particle that's emitting light. She's shining it, and then you can kind of see that all the areas around her, like, they're very dark, but you can still make them out. And that, I imagine, is because of that dynamic kind of global illumination light bouncing.
Still having beautiful bounce lighting. Dynamic illumination...
Yeah, and you can see that specular reflection that he's talking about.
Means specular as well, which you can see on all the
specular reflection
surfaces.
that he's talking about over all of this stuff.
You can even see the Niagara-powered bugs reacting to the light.
Yeah, and then the fact that the particles are reacting to the light as well is
Lumen
really cool.
not only reacts to moving light sources, but also changes in geometry.
Yeah, well, yeah, I imagine so. Then, of course, it's dynamic. Yeah, the falling rocks sound really good, by the way, but also you can see that's what I was talking about. Like, you can bake lighting for a scene and it can be perfect and it can look great, but if you need to like remove part of the scene like this, especially if it's not like in one go, but you can see these rocks are kind of gradually like falling away. If we just rewind a little bit. Yeah, so you can see that the rocks are kind of they're falling slowly away and revealing this stuff. And as that's happening, like the scene's getting brighter. I love the lighting on the actual rocks falling as well. Looks really, really good. And yeah, there's that hole up there. Yeah, really cool. And you can see it completely changed the lighting of the whole scene, right? Like it's now just completely
Remember we mentioned high
lit.
poly assets? This statue was imported directly from ZBrush and is more than 33 million triangles.
Wow.
No baking of normal maps, no authored LODs.
Yeah, so that's great. So no normal maps on this at all, and no LODs, no level of detail kind of models, which is, two things we could talk about there. But essentially, the point of this, I think, is to basically say that you can take this amazing high quality model that, artists don't even have to worry about their poly counts, their triangles. Like, I mean, they probably will, on one hand, because I feel like if you had this in Maya or in Blender or something like that, and it was that many triangles, it's just going to make it very difficult to work with. But even if Unreal Engine can handle it, maybe the other tools necessarily can't. But anyway, having to not worry about this, having the ability to sculpt and model and do all of that stuff with basically, seemingly infinite detail, that's really cool because it means that you don't have to then go through and create all of these LODs, all of these kind of level of detail models, which are basically just, lower poly count versions, lower quality versions of this original model because you need them for different rendering scenarios, like if the camera's very far away from this actual model. Being able to get your like source asset and just drop it in and have Unreal Engine take care of the rest in real time, right? In the runtime is amazing. And there's baking of normal maps as well. Normal maps are something that we use to basically simulate more triangles than there actually are. So you can apply a texture which has like per pixel basically data, which says where like certain triangles, certain fake triangles, where their normals would be if they were there. And obviously if we have 33 million triangles, we don't need normal maps because we don't need that kind of, cheat way of getting more detail because we have more detail.
And we can do more than a single statue. There are nearly 500 of that exact statue at the same detail level placed in this room for a total of over 16 billion triangles.
That's amazing.
Statues alone.
That is amazing. Just having to sort through all this data, like, I mean, these are instanced and everything, but like, I'm sure that this demo is probably like over 100 gigabytes, if not hundreds of gigabytes, because there's so much, texturing, so much too many triangles, so much data. So just reading that data, you know, that's why it's interesting to look at the PS5 architecture as well. I'm sure that a lot of this is obviously being streamed in from disk every frame. That disk, that SSD has to be blazing fast. I don't know what technology they're using, but that like relation between disk and then, you know, VRAM and all of that stuff has to be really tight. And I think that might be even specific to this architecture.
There are hundreds of billions of triangles.
Yeah, really cool.
So with nanite, you have limitless geometry, and with lumen, you have fully dynamic lighting and global illumination.
Yeah, that looks
all
amazing.
Running on a PlayStation 5.
I should probably have looked at the PlayStation 5 specs and architecture before this video, but I'm assuming that's probably released by now. But yeah, it looks absolutely amazing. And I also wonder what resolution this is in. I'm watching it in 4K, so I assume maybe they're rendering it in 4K. But yeah. Oh, look at all that detail. That's really, really amazing. I like how just everything's falling apart around her, because of course that makes the technical demo seem better. But she's really not having a good day.
And this doesn't need to be constrained to small rooms. It can stretch all the way to the horizon.
I was waiting for this. I mean, I've already seen this demo, so I know it's coming, but I'm still waiting for it. Yeah, wow. Look at that.
Don't fail me now.
Yeah, that's so much stuff going on. I feel like we should almost go through this frame by frame. Their motion blur is pretty nice. Oof, look at those rocks. Yeah, that's really cool. Also, it's kind of hard to tell because obviously this video is compressed and put on YouTube, but some of the artifacts like I'm seeing probably with video compression, it's difficult to say, like tell if they're actually noise within the renderer or if they're actually just video compression. I'm just assuming the video compression though. Some of them are probably noise. But yeah, this looks phenomenal. This looks like a movie. This looks like it's been, you know, this looks like it's been offline rendered for sure. And the thing that strikes me as well is that you have to remember that this is not just rendering. This is not just a scene that's been completely scripted and it's not just being rendered. A lot of this is actually, well, it's interactive, right? The fact that it's interactive, the fact that all of this has to be simulated and, you know, kind of computed in real time, you know, rendering aside, that's also amazing. And obviously with the kind of billions of triangles that they're talking about with source geometry, there's more to that than getting it on the screen. You know, obviously it has to interact with the environment around it and with the player. And that's a whole nother problem of kind of dealing with models and dealing with assets of that high fidelity, high quality stuff and making them, you know, also be interactive and all that stuff, you know. Not just the rendering that is impressive here, for sure. Depth of field is pretty nice as well. They've always had good depth of field, though. I think that's really important.
It's
That looks
time
nice.
to see what's next.
Yeah. Well, that was probably rendered in real time as well. Yeah, that's amazing. 2021. That's a while away. All right, so yeah, my final thoughts on this are it's incredible. Like, it's really good. There's a level of detail here that we just probably, like, I don't think we've ever seen before in any game engine. I think that they've taken all of that Fortnite money and actually like put it to very good use, because this stuff is for sure industry-leading technology. You know, being able to deal with that amount of source data in real time and kind of work out what you need, what you don't, how to put that on the screen, how to make it interactive, that's a huge problem, and they're solving it, like, well, seemingly very well. I can't wait to actually dig through this and see how it all works. And I think they did mention like a technical breakdown would be coming, so I'm really excited for that. If you guys want to see me talk about that as well, drop a comment below. But in general, yeah, like, what do you guys think about all this tech? You know, leave a comment below to what you think the most impressive part of this was. I mean, there are so many, but I am interested to see what you liked most of all. If you did like this video and you want to see more of this stuff, don't forget to hit the like button and subscribe to this channel. Thank you guys for watching. I will see you next time. Goodbye.